Sorry, I'm going to go a little out of order here. I don't know if I put these slides out when I recopy them in. So I'm going from the video slide down about 4, 5, 6, it looks like, to consolidation. And so we now know that the hippocampus isn't involved just in storage of memories, and in fact doesn't appear to be as involved in the storage as we expected, but does rather there is this connection between the hippocampus and the cortical regions that seems to be required for the storage that we think of when we think about memory systems. What we now know is that the hippocampus, this connection between the hippocampus and the frontal cortex, is involved in this process called consolidation. And consolidation is necessary for memories to become sort of stamped in, if you want to call it that, into your long-term memory store. So in order for it to have a very strong memory trace that lasts over time, for it to last beyond the reversal of your short-term memory store, for instance, it needs to become consolidated. And once fully consolidated, then it is now a strong memory trace that is likely to stand the test of a good deal of time, at least. And so we know that what happens with consolidation is something along the lines of what's demonstrated here in this figure. And so on the bottom, this is representing the hippocampus, and the top is representing the cortical regions. And what this is demonstrating as the standard model of consolidation, that's a current model of consolidation. No doubt it's also going to continue changing over time to some extent. But the current model suggests, and notice we have time on the x-axis here. So early on, first in interaction, first encoding of a memory, for instance, or even days later, for instance, the memory does in fact reside largely in the hippocampus. And that is, in fact, where that memory is stored. So early memories, if you want to call it early memories, are stored in the hippocampus. And you can then see that there are strong connections between the hippocampus and the cortical regions. Now, we are not sure whether this is required for the memory to exist. More likely, it seems to be that the hippocampus is speaking to the cortical regions that are involved in attention, planning, thinking, and whatnot, reasoning, decision-making, and that likely that these interactions between the two are a complex relationship between the two that are helping to drive all of those types of higher order cognitive processes. Yeah.
Is it kind of like the loops that you talked about? Are they interacting?
No. Well, the question was, is it like the loop? So I think I mentioned about like these feedback loops where every brain region is sort of informing the other of what's going on.
Loops that you talked about last week, the chronological or whatever, you know how they overlap on something about those.
No. In fact, no. But good question. So I'll clarify. So the question was, is this representative of, say, that when we talked in last class about the different long-term memory stores, the phonological loop and the visuospatial sketchpad, and then the central executive in between? Technically, this will no. So the vision, those three are actually that's 2 classes ago. Now that I think about it, and those are working memory concepts. So the working memory system is believed to now be broken up into several working memory stores, one of which is the phonological loop, one of which is the visuospatial sketchpad, and the central executive that sort of manages your working memory systems. And that central executive, just a review for you guys, and the phonological loop and the visuospatial sketchpad are sort of involved in retaining in current memory what is most required within reach. I used the desk analogy, and it was like things you could reach for right away, things you needed in your immediate environment, visual and spatial information in the visuospatial sketchpad, oral information in the phonological loop, oral and linguistic information in the phonological loop, and then the central executive sort of manages the involvement between the two of these. This, to get back on topic, is your long-term memory store. So to relate them together in one process, you are sitting at your desk and you're trying to, you have all your stuff organized and the stuff that you need is within reach, and you're rehearsing, for instance, what you want to keep in your long-term memory, or in your short-term memory, your work memory. So you're rehearsing a phone number. Again, 967-1111, 967-1111. You're trying to rehearse that. That rehearsal process will keep it in your working memory store. In order for it to transfer to long-term memory, we talked a lot last class about things like depth of processing and whatnot that will aid that will facilitate the transfer of information from short-term into long-term memory. When it gets encoded into long-term memory, the arrow that goes from short-term to long-term is an arrow you can think of as an arrow heading to the hippocampus. Okay, so when it goes to the long-term memory store, it's going to the hippocampus. Okay? Early memories, that first time, and while they remain early in their memorial stage of things, they do reside in the hippocampus, and there are strong connections between the hippocampus and the cortical regions. As time goes on, you notice that the connections between the cortical regions and the hippocampus are starting to decrease. They're minimizing. They're not as required. They don't occur as often. And you can start to see that some cortical regions are starting to talk to each other. And this is indicative, first of all, this is actually how it seems to be working in the brain. But you can also think of it from a representational perspective of the memory sort of going from storage in the hippocampus to storage in the cortex. And you can kind of think of this from an analogy perspective. You can actually think of your hippocampus as your file cabinet in the corner of your office. So your short-term working memory is what's on your desk. Your hippocampus is the file cabinet in the corner. And your cortex is your archive system, the library down in the basement, something along those lines. Okay? And so when you think you might need something, it's not in current working memory, but it's still an early memory, and it's something that's just recently been remembered. You might want it in your file cabinet in your office type of thing. You want it in your hippocampus. Once it's a long-term memory that has consolidated, you can put it down in the basement in archives and retrieve it when you need it. If you put it in archives too early, as the analogy goes, you might forget you put it there, and the long-term memory trace may not, and the trace may not exist. That connection may not exist. And then as time goes on, the process continues further until you can see in these dots are largely representing minimal to no further discussion between the hippocampus and the cortical regions. We have dotted lines because they're, I say, minimal. These regions are still talking to each other, sort of like all brain regions are talking to each other in many different ways. But in terms of remembering a given memory system, these connections are no longer important. And the discussion between the cortical regions is now paramount. And so it's now understood that when you recall a memory, you can recall it from either your hippocampus, orange bar, or your cortical regions, blue bar, depending on how recent the memory is. And so we have here a recent memory, and if we use MRI and we would evaluate in the brain what was active as they were recalling the memory, you see that with the recent memory, people who remember the memory will show hippocampal activity during that retrieval process. Of a more recent remote memory, people can still remember it, but when they remember it, they're now showing cortical activity, and the hippocampus is far less involved in that process. And so we refer to the second set of bars here, we refer to B as an example of a memory that has now been fully consolidated, to use the terminology again. Once it is stored in archives, once it's in the cortex fully, once the connections between the cortex and the hippocampus are no longer required, that would be the definition, the neural definition of full consolidation. Does that all make sense? Is that relatively clear? Good. Okay, I'm going to go back now. I could have gone in order, but I think it was easier to explain it that way. So I'm going back to the second slide now, right after the video. So so I've talked about consolidation. That consolidation process that I just talked about is what's referred to as system consolidation. So, and by system, we're talking about the entire brain system. So, from a macro approach level, from a system level, consolidation occurs when information is now held in the cortex rather than the hippocampus. There is also what's referred to as synaptic consolidation. We're going to talk about it much less. That's why I went on to the other one first. But just to indicate that when you're actually forming a memory, what's actually happening is there are changes in the synapse that are occurring, that are representing that learning process. So you'll remember from early on in the course, the synapse is the space between the dendrites and the axon of neighboring neurons, and that the way that they transmit information is that information flows down the axon of one neuron, releases chemicals into the synapse. Those chemicals bind to receptors on the dendritic spines of the postsynaptic neuron, and assuming everything works properly and the neurotransmitters release the appropriate levels, the electrical current will continue down the next neuron. Hopefully you all remember most of that. Does everybody remember that? Yeah, okay. So what this is representing is the axon button of neuron A, the dendritic spine of neuron B, and the synapse between the two. And we're looking at a fairly simple diagram that's demonstrating that. What this is demonstrating is action potentials. Okay, so each spike here is an action potential in the second neuron. And so we're not going to get into a great deal of detail. All you really need to know, you'll notice that in the diagram, there are changes occurring at the level of the synapse. And the changes are occurring, not just there's changing in the synapse, which is represented by more blue arrows in the synapse, which is indicating more neurotransmitter release. They are represented by changes on the presynaptic axon, as indicated by the different bumps and wiggles and whatnot. You can see it's smooth over here, and becoming squiggly and wiggly as you go along. And so that's representative of changes to that axon. And those changes, they're represented as these little squiggles and wiggles, but they really are that way. And that represents different receptor and different release points for neurotransmitter release and whatnot. And then they're also represented by changes similarly on the postsynaptic neuron, and the dendrite of B, also just represented by differences you can see in the bumps. And that's also represented by different types of receptors and different branches off your dendritic spines and whatnot. Don't need to know a lot more detail than that, but I do want you to know that there are changes at the level of the synapse, and there are these multiple types of changes. So all of the presynaptic, the postsynaptic, and the synapse, and all change, and that those changes, what those changes are, is indicative of the process of learning, forming a new memory. So as a memory is formed, these changes occur. And then what this is demonstrating is the first presentation of a stimulus. You can see what's happened is the stimulus has activated the neuron and has led to action potentials that have gone through. And so that's indicative of a successful processing of the stimulus. With continued presentation of the stimulus, we see